You know, have you ever looked at one of the world's biggest problems and just felt like you're missing something? Like there are all these hidden layers you just can't see all at once? Well, today, we're going to dive into a brand new framework that could totally change that. It gives us a way to see the world's hidden patterns across every single scale at the same time. So, yeah, let's get into this powerful new way of seeing.
So to really get this, let's start with a huge, almost impossible problem: governmental corruption. I mean, think about it. It's not just one single act, right? It can be this tiny little change on an invoice, or it can be as massive as capturing an entire state's government. It's happening on so many levels at once that trying to see it all is like trying to focus on a single leaf in the entire forest at the exact same time. And the scale of this, it's just staggering. The World Bank estimates that $1 trillion is paid in bribes every single year. A trillion. It's this massive problem that's hiding in plain sight, and the reason it's so hard to catch is because it operates on all these different timelines and scales.
And that brings us right to the core idea here. Corruption isn't just one thing, it's what we call a multi-scale problem. It goes from the really fast, specific stuff all the way to the incredibly slow, systemic rot. You can almost think of it like different sound frequencies all playing at once, creating this one complex, messy chord. Okay, so check this out. This slide just lays it out perfectly. Look down at the high frequency band. These are the fast-moving crimes, the things happening over just days or weeks, like a little bit of invoice fraud. Then in the middle, you've got the mid-frequency stuff, like bid rigging, which plays out over months. And then way up at the top, that low frequency, that's the slowest wave of all. That's systemic capture, and that can take decades to unfold. So the question is, how could any one tool possibly see all of that at once? Well, the answer is a totally revolutionary AI framework that is designed to do exactly that. It literally teaches a machine to see the world not as one flat picture, but in these distinct, overlapping frequency bands all at the same time. This right here is the best way to think about it. It really is like giving AI a pair of special glasses that splits its vision into 3 layers. And suddenly, you can focus on the background, the midground, and the foreground all at once without losing track of any of them. That's exactly what this framework does for data. So that first layer of vision is the low frequency band. This is like the 10,000-foot view. It's what captures the slow, deep currents, the systemic biases, the long-term trends, the whole structure of a system that changes over years, maybe even decades. Next up is the mid-frequency band. This is where you see the patterns that are kind of in between. They're not the tiny details, but they're not the whole big picture either. Think of things like recurring procedures, like procurement cycles, or the distinct shapes of different objects in a scene. And finally, you zoom all the way into the high-frequency band. This is where the AI sees the really fine-grained texture of reality, all the rapid individual events, the tiny little fluctuations. In our corruption example, this is that single fake invoice. In a photo, this would be the actual texture of a piece of fabric. Okay, so the official name for this tech is the Universal Signal Decomposition Framework, or USDF for short. And that word universal is everything. This isn't some one-off trick. It's a principled architecture, which means it's built on these deep, solid concepts from signal processing and neuroscience. It can learn these multiscale representations from pretty much any kind of data you throw at it. So how in the world do you actually build this? How do you teach a machine to see the world in this incredible, layered, multi-frequency way? Well, the blueprint for it is actually surprisingly elegant. It all works in 3 pretty simple steps. First, you just feed the AI the raw data. Second, a part of the AI called an encoder chews on that data and spits out a compressed digital code. And then third, and this is the magic part, the USDF framework grabs that code and intelligently sorts it into those 3 frequency bands we've been talking about. So how does it do that sorting? The secret sauce is a technique called differentiated regularization. Now, I know, that sounds super complicated, but the idea is actually really simple. The AI just applies different rules to each frequency band. It learns that not all information should be treated the same way. This table shows you exactly how. See that beta weight column? You can just think of that as how strict the rules are. The low frequency band, the big picture, it has the highest weight, a perfect 1.0. This basically forces the AI to be really, really disciplined about learning that global structure. Because in the real world, big structures are usually pretty stable. But then as you go down to the high frequency band, the weight drops to 0.5. That gives the AI way more freedom to capture all the messy, random, fine-grained details of life. Okay, so remember when I said this was a universal framework? This is where things get truly mind-blowing. Because detecting corruption, that was just the starting point. This way of seeing the world applies to almost any complex system you can possibly imagine. Take neuroscience. This framework pretty much mirrors how our own brains work. It can take brain signals, EEG, and break them down into their natural frequency bands, from the super slow delta waves for deep states all the way to the lightning-fast gamma waves tied to perception. It's literally learning the brain's own language. Or how about medicine? It can analyze a single heartbeat. The low-frequency band can spot long-term heart rate trends, the mid-band can catch arrhythmias, and the high band can spot tiny, tiny changes in the heartbeat's shape that could warn of a future heart attack. It's like a complete physical from just one signal. For robotics, this is an absolute game changer. A robot can use the low-frequency band for its big-picture mission plan, like go to the kitchen, while using the high-frequency band to manage the super fine motor commands for its joints in real time. It creates this incredibly stable, layered control system. And maybe most important of all, climate science. USDF could finally help us solve that core problem of separating the signal from the noise. The low-frequency band can pull out that long-term climate trend, while the mid and high bands capture the natural seasonal cycles and all the individual weather events. There's this quote from the source material that it perfectly sums up the entire philosophy behind this whole thing. It's a deep idea, but it's also really simple. Our tools for understanding the world really ought to match the way the world actually works. So when you bring this all together, why is this so much more than just some clever new algorithm? Well, it's because it represents a huge shift in how we can even approach solving our most complex problems. The upsides are just immense. The models it creates are way more interpretable because each band has a clear job to do. They are naturally multiscale, obviously. They're flexible enough to be adapted to any field you can think of. And they're grounded in decades of real, solid science. It's not just another black box. It's a principled new tool for discovery. So look, if there's one thing you take away from all of this, it should be this. We are swimming in data these days, but more data alone is not the answer. The future of solving really big problems is about finding the right lenses, the right frameworks to see the hidden, multi-scale architecture of reality itself. And that really leaves us with one final fascinating question. I mean, think about financial markets, social dynamics, the mysteries of biology. What other incredibly complex problems could we finally crack if we could see all the scales all at once?